Hello, everyone. My name is Camila Novaes. I am a postdoc at the National Institute for Space Research in Brazil. First of all, I would like to thank the organizers for the invitation and for the opportunity to talk about my recent work. In this talk, I will show you how we can use higher order statistics and combine them with simulation-based inference approach to maximize, to increase the cosmological information that we can extract from the data. So in this talk, I will start with an introduction and the motivation of why we should use higher order statistics and how we can combine them with simulation-based inference. And we'll show you an example of how we can apply these tools to real data. And we'll conclude with some main points. So I will start showing you this summary of the history of the universe, starting with the release of the cosmic microwave background radiation and the steps that the universe have been going through after that until the later universe that we observe today with our surveys. So we usually say that cosmology is a statistic, but why do we say that? The point is that we believe that the seeds for the large-scale structure that we observe, they come from they come from a stochastic process in the beginning of the universe, and for this reason, we cannot trace back the position of a given object that we observe. We cannot know the position of one galaxy at the beginning of the universe. Although we can model their distribution, their statistical information. Here, an example is the two-point correlation function. This two-point correlation function can be calculated from a distribution of galaxies, for example, in the following way. We can calculate the distance between each pair of galaxies in our dataset. And we can, by doing a kind of histogram of these distances, by counting how many pair of galaxies are far from each other by a given distance, we can map the axis of probability of finding a pair of galaxies distanced by a given scale. So this is the two-point correlation function, which we can model very well with our theory. But this is in the real space, and here is an example of this two-point correlation function, calculated from a set of galaxies. But we can also translate this information into Fourier space, which I show an example here in this plot. And we can also consider, we can also translate this information into harmonic space, calculating our angular power spectrum, which is very commonly used for CMB analysis, but also for the galaxy distribution, where we project in the sky a given range of redshift of our tracer. So given that we can model very well our two-point statistics, which is our traditional method to constrain cosmological parameters, to do cosmology. Here is a very simple illustration of how we do this. We have our data, and from our data, we can calculate the two-point statistics. And we can model these statistics by Boltzmann code, for example. And by fitting our data with this model through a Monte Carlo Markov chain method, we can find the best fit of the cosmological parameters that we are interested in. But the point that I would like to emphasize here is that this process usually need assuming a given model for the likelihood of the data. And usually we consider it to be Gaussian. And in fact, this is very nice. This works very well for Gaussian fields, like, for example, the CMB data. But what about the other data? So this is why I would like to call your attention for the following. In the beginning of the universe, when the CMB is released and we have the small density fluctuations, we have these fluctuations evolving with the evolution of the universe. And because of the gravitational effect, they start clustering, and they are clustered like what we observe today. So, in this process, from the beginning of the universe, where these density fluctuations were of the order of 10 to the minus 5, until today, these density fluctuations have grown orders of magnitude. So when we are trying to map the distribution of dark matter by using these tracers, measuring these tracers of the dark matter, we are actually dealing with this kind of density fluctuations, these larger density fluctuations. This means that from this point in the history of the universe to this point, the large-scale structure has been through a nonlinear evolution. And this made this, what was initially Gaussian or nearly Gaussian, very non-Gaussian today. So to analyze CMB data, we can indeed use two-point statistics because they are almost Gaussian, so that these statistics carry all the information. But for matter tracer, where we definitely don't have Gaussianity, these statistics will not tell us everything about this tracer. We would need to go beyond. We would need non-Gaussian statistics to fully describe it. Actually, the high-order statistics are useful also for CMB analysis. In the case, for example, when we are interested in measuring possible deviations from Gaussianity, the called primordial non-Gaussianity. And in this case, we need to go beyond the two-point statistics to be able to detect this tiny signal. And for large-scale structure, for the matter tracers, this is even more important. So here's an example. We have here in the first plot a Gaussian map, and below we have a non-Gaussian map. And here in the right, you can see the histogram distribution of the pixels of each of the maps. And you can see that they are very different. And the red one coming from the non-Gaussian map, it is very non-Gaussian. It has a very non-Gaussian distribution. But still, we can see here from the angular power spectrum calculated from each of them that they agree very well. So this is an example of how the two-point statistic is not giving us all the information. So this is why we need to go beyond the two-point statistics. Here I list several of possible high-order statistics that can be used and that are being explored by literature. Here in this first part, we can see some examples of any-point functions beyond the two-point. So the three-point and four-point, called the bispectrum and three-spectrum in harmonic space, for example. And here in the middle, we have some examples of other non-Gaussian statistics, like the Minkowski functionals, the peak counts, minima counts, probability distribution function, and scattering transform. These are just some of the possible statistics. And I will mention a bit more about some of them later. And here in the last part, I also would like to mention that another possibility is that instead of using a different tool, you can still use your two-point statistic, but before calculating it, you can transform your cosmological field through a nonlinear process, a nonlinear transformation of the field. This will bring the non-Gaussian information to the two-point statistic. And a possibility for doing this is by log transforming your cosmological field or by using what we call marked power spectrum. So if we get back to our traditional inference analysis, how we can use the non-Gaussian statistics in this process? We could, for example, instead of using Gaussian statistics, we could put here the non-Gaussian statistic. But the point here, the main problem is that many of these non-Gaussian statistics, they don't have an analytical expression. So that we are not able to calculate the theoretical expectations for this statistic. So if this is not possible, how can we do this MCMC method to infer, to calculate the best fit of the parameter, of the cosmological parameters? So a possible way of doing this is using an emulator, so that instead of calculating the theoretical expectations for these summary statistics, for these non-Gaussian statistics, we are actually using an emulator trained over many simulations that are simulated over a wide range of cosmological parameters, which means that for each of these red dots, we would have a set of simulations, and we would use these simulations, these forward modeling simulations, to train this emulator, so that instead of calculating the summary statistic for a given cosmological parameter, we would emulate this summary statistic, this non-Gaussian statistic, and then again compare this emulated summary statistic, this emulated non-Gaussian statistics, to what we calculate from the data. And then the other parts of the method would be the same. But the point here is that even using this emulator and using our non-Gaussian statistics, we still have to assume a likelihood for the data. And again, in many cases, we still assume Gaussianity. So how could we overcome this step? How could we avoid assuming any likelihood for the data? A possibility is to do what we call simulation-based inference, so that we don't emulate anything, but we consider a neural network, for example, here, to map between the summary statistics and the cosmological parameters. So you would give to this neural network both of them. You would give the non-Gaussian statistics calculated from a lot of simulations and the cosmological parameters that to which they correspond, so that they will learn the relation between them. And then you give to the trained model the summary the non-Gaussian statistics that you calculate from the data. And since this method is already trained, they would recognize the pattern of these non-Gaussian statistics and then predict which would be the cosmological parameter. So this is the pipeline that we use for the example that I am going to show you in the next slides, and it will be a bit more clear each of the steps that we consider. And the important, the nice thing here is that this can be applied to any kind of data, and not only in the specific case that we are considering this example. So in this example that I'm going to show you, we are applying this kind of pipeline to weak lensing data. So before going to our analysis, I am going first to motivate our purpose here. So we have here in the middle an image of simulation of the dark matter. And as we know, we cannot measure directly, observe directly the distribution of dark matter. And to do this, we use tracers. For example, we can use 21 centimeter intensity mapping. We can also use galaxy clustering to map this distribution. And also we can use weak lensing. So we have here these two regimes of gravitational lensing, where we have the background galaxies with their lights distorted by massive objects in front of them. So we have here this strong regime of gravitational lensing. But what is very interesting for cosmology is also this weak lensing regime, where instead of considering this strong effect, we are considering the effect in this region far from these massive objects. So if we zoom in these slice, we can see here the distribution of galaxies, and just by eye, we cannot say if they are suffering of the gravitational lensing. But if we measure the ellipticity of each of these objects, and then we average over the ellipticities, we will get as a result something parallel to these black lines here, which is tangential to this massive object. So this shows us that each of these objects are in fact suffering from this gravitational lensing. But the point here that I would like to show you is that how difficult it is to measure the ellipticity introduced by the gravitational effect. Because what we measure is the total ellipticity, which corresponds to the intrinsic ellipticity, which means how we observe this galaxy, and the shear, which is this parameter, which corresponds to the ellipticity introduced by the lensing effect, which corresponds to just around 1% of the total ellipticity. And to model this observation, we also use some bias parameters to take into account other effects. So when we are able at the end to measure this ellipticity introduced by the gravitational effect, this shear, we can translate the shear effect into the convergence information, into a convergence map, where these red spots are related to massive regions, while the red spots are related to regions with less mass. So how can we do cosmology using this convergence information? The convergence can be modeled, can be written directly in terms of the density of the density fluctuations, the density of matter. So for this reason, we can use them to constrain parameters as the density of the matter in the universe, and also the sigma 8 parameter related to the amplitude of the clustering of matter. And since the two parameters, they are degenerate, because of this degeneracy, it is common to combine the two of them into just one parameter, this S8 parameter, which will give us information about this amplitude of the matter clustering. And then we measure this parameter. So if we get back a few slides and get this plot that I have shown before, we can see here many observations of this matter power spectrum. And all these measurements of the matter power spectrums, they are fitted with the cosmological model, with the standard cosmological model. And we have here measurements from CMB surveys and also from large-scale structure surveys. But if we get all these measurements and translate them just into the amplitude of the power spectrum, and then bring all these values here to this other plot, we will see here estimates of the S8 parameter coming from CMB surveys and measurements coming from large-scale structure surveys. And we can see from this plot they seem to be in tension. There is this discrepancy between measurements coming from high redshift and measurements coming from the low redshift. But why is it important for us to understand what is happening? Why they are not in agreement? Because when we measure this S8 parameter from both instruments, we are measuring this parameter from density fluctuations from completely different epochs of the universe. So here, to go from here, from the beginning of the universe to the later universe, these density fluctuations have grown a lot and experiencing gravitational effects, so that by understanding what is happening here, we can learn a lot about the evolution of the universe, their content, and how gravity are acting during all this process. So what about we do this, we estimate this S8 parameter, but not using 2-point statistic, but using higher order statistic. And we do this using the data of the first year of the Subaru Hyper SuperChem experiment. Here I am showing you the 6 disjoint regions observed by HSC, which corresponds to the deepest lensing data among the ongoing surveys. I am showing here the 4 redshift beams that are available in this data, but we are not considering this last one because we believe that there is some possible unknown systematics. So we are considering just the first 3 of them. So at the end, our purpose is to estimate not only the S8 parameter, but also the omega m parameter. So here I would like to show you our team and the previous results that are coming from the effort of everyone here. And here we can see that many of these works are using many different higher order statistics. And we can see here that they show how powerful the high order statistics can be, showing that they can improve results coming from Gaussian statistics, from the 2-point statistics by, for example, 35% in S8 parameter. And similarly, all the other higher order statistics. So in this case here, all these results are coming from analysis using that emulator that I mentioned before. So here, all these results are obtained emulating the summary statistics and still using a Gaussian approximation for the likelihood of the data. So our next step was exactly try to avoid this assumption of Gaussian for the likelihood. We don't do any assumption for this likelihood by using simulation-based inference. So this is a summary of all the process, and I will talk a bit about each of the steps. But the important thing to mention here is that all the steps that we consider for our simulations, we also consider for our data. And this is important to estimate and to compare the same things at the end. So let's start showing you how we simulate our data. So our simulations span a large range of cosmological parameters values. So we have here S8 parameter and omega m parameter, and we have 50 realizations, 50 simulations of the HSC data for each of these dots. And all of these simulations will be used to train our model. We have this additional set of simulations, the fiducia one, which corresponds to a larger set, corresponding to this pair of parameters here. So the important point here to think is that all the simulations have to reproduce the characteristics of the data. So all of these characteristics that we have from the data, we have to include by mimicking our simulation, our data. We produce the simulations by mimicking what we have from the data. So after producing our simulations, mimicking our data, we have now to calculate the summary statistics. And we consider here not only non-Gaussian statistics, but we also consider the 2-point information from the angular power spectrum. From the non-Gaussian statistics, we are considering the peak counts and minima counts, which corresponds to counting the number of pixels whose surrounding 8 pixels have smaller values, or in the case of minima, the opposite, higher values. And the Minkowski functionals, which corresponds to 3, to fully describe the 2D cosmological field that we are considering. They are topological describers of this field. And the left of them is the probability distribution function, which is basically a histogramming of the pixels of the cosmological field, of the map that we are analyzing. So after simulating them, calculating the summary statistics, we have this additional step here of compression of the data into just 2 values. What do I mean by that? Here, this compression is performed using a neural network. So we have here our parameter space that we are sampling with our simulations. We give, from the simulations, we calculate the summary statistics, and we give these data vectors with the summary statistics to the neural network, together with the corresponding cosmological parameters. So the idea here is to use this neural net to map between the summary statistics and the cosmological parameters. So it will learn what happens with the summary statistics when I change the cosmological parameters. In this way, when I give it the data, it will predict which would be S8 and omega m from the data. So this is what we do for this compression. So the motivation to do this compression is the following. When we combine all the summary statistics that we are considering here, we would have a data vector with more than 300 elements. And this is too big to be dealt with at the end of the pipeline. So before going to the end of the pipeline, we first do this compression in just 2 numbers. So after compressing our summary statistics from the simulations, we use this compressed data, or these predicted values of the cosmological parameters. We use it, and we use this compressed data together with the true values of the cosmological parameters as input to a neural density estimator. This NDE is intended to, this can be used in different ways. For example, we can use it to learn the likelihood of the data. And what we do here is to use it to learn the posterior of the cosmological parameter. So we give it all this data, the compressed data from the simulation and true values of the cosmological parameters as input. And from them, it is able to learn the posterior distribution. So after training this NDE, we can now apply it to the compressed data coming from the observation, the real observation. So when we apply this trained model to this data, to this compressed data, we then estimate the posterior, the learned posterior for the cosmological parameters. So before showing you the results that we get from the data, I would like to discuss a bit about what happens if our data have systematics that we are not accounting for in the simulations. So to check here what happens, we produce other sets of simulations including different systematics and apply our trained model to each of them. For example, here in the first case, what happens if our real data have redshifts that are calculated using a different model for the photometric redshifts? So in this case, when we use different models to calculate the photometric redshifts and then generate our convergence field and calculate our summary statistics, if we apply our trained model over these new simulations, we see that the S8 values estimated using this pipeline applied to these new simulations, the average of the posterior are not far from the expected values represented by this dashed line. The error bars here represents the 1 sigma distribution of the 1 sigma range of the posteriors. So we do the same test for other systematics, for example, a miscalibration of the multiplicative bias, where we consider what happens if the multiplicative bias that we assume for our simulations, what happens if it is a bit larger or a bit smaller than we used for the simulations. And again, no significant bias is observed. And we do the same thing considering baryonic feedback, which is not considered for the simulations we use to train the model, and also different values for this parameter representing the intrinsic alignment. So in all these cases, in both cases, combining all the summary statistics, Gaussian and non-Gaussian, or using only the non-Gaussian statistics in both cases, and for all tests we consider, we don't see a bias larger than 0.17 of the 1 sigma range. So one important thing to point here is that our pipeline of choosing, for example, the smoothing scale that we apply to the convergence field, or the scale cuts that we apply to the Gaussian or non-Gaussian statistics, all of these are chosen based on the results that we have here to assure that in case our data have non-systematics, our results will not be affected by them. So these are our results from analyzing the data for omega m and here for S8. And in both cases, we can see how combining all the statistics improve the results obtained from using only the Gaussian statistic, only the angular power spectrum. So here we have an improvement of 40% for omega m and of 26% for the S8 parameter. And one interesting thing that we can see from here is that the constraint obtained using all of the statistics combined and the constraint coming only from the non-Gaussian statistics, they are very similar. which means that the 2-point statistics not adding too much information to what we already have from the non-Gaussian statistic. So here we can see the results. These first three are the results that we already saw in the first slide. And these are the results here, the average and the 1 sigma of the posterior measuring the S8 parameter from the data. We used here we show here results using only each of the non-Gaussian statistics individually and their combination with the angular power spectrum. And we can see in all the cases, we have results that are in agreement with each other. And here in parentheses, you can see how the results obtained from how the constraint obtained using the angular power spectrum is improved using these other statistics. So, for example, results obtained using Minkowski functional are 24% better, have a 24% error bar smaller than the error bar than the constraint obtained using the angular power spectrum. So comparing all of them, we see that the Minkowski functionals, they are the main, they seems to be the main driver of this improvement. So if you compare all the 4 summary statistics that we are considering here, we see that the Minkowski functionals have the highest constraining power, and the last of them would be the 2-point statistics, the angular power spectrum. So one point that I would like to highlight here is the fact that in the case of the angular power spectrum, even after applying some smoothing scale, we still have to cut some multiples, some higher multiples, to avoid biasing our results by systematics. But for the non-Gaussian statistics, we didn't need to worry about this. No bias was introduced, and we didn't need to cut more scales with them. So here we have a comparison of all our results using different higher order statistics. And here we have the results obtained using higher order statistics combined with simulation-based inference. We see here a good agreement among all of them, and also with other measurements coming from other surveys of weak lengths, measuring weak lengths. So to summarize our findings here, we see that this pipeline, this combination of higher order statistics and simulation-based inference seems to be quite robust against the systematics, considering the pipeline we use here. We also confirm this high constraining power of the higher order statistics when we compare our results with those obtained using only the angular power spectrum, only the 2-point statistic. And we also show how easy can be the combination of several summary statistics. Because you can imagine how difficult it would be, for example, in a traditional inference pipeline where you would have to construct your covariance matrix combining all of these statistics. This wouldn't be an easy task to do. So here it is relatively easy to combine all of them. We just need to use a compression in the middle of the way. And finally, we see that this combination of higher order statistics and simulation-based inference, it seems to be competitive and feasible, even in the case we consider here with limited number of simulations, because the ideal for this kind of method is to have as much simulation as possible. And even with this limited number of simulations, we still have good constraints of the cosmological parameters. And this is a particularly challenge for Rick Lindsay because these kind of simulations are quite expensive. So to finish, I think the main takeaways that we have from these all these discussions is that this combination of higher order statistics and this simulation-based inference approach, it is this combination is required to assess all the information that we can access from the data, all the information that this data can provide us. And this SBI, this pipeline, this SBI and the high order statistics is particularly promising in the context of the next generation of surveys. And also, I highlight here again that a combination not only of different summary statistics, but summary statistics from different probes would also be possible with this pipeline, with this idea of inference analysis. So to finish, we also have to be realistic because all this training process, all this pipeline, it relies on having simulations, a large set of simulations and simulations good enough. And that reproduce enough the data and the systematics that we have in the data. And this is also not an easy task. So we have all these possibilities from future surveys, but we will also need these simulations to make this kind of pipeline possible in the future. So thank you all. I'll finish here, and I thank you all for listening. And thanks again to the organizers for such amazing conference.